Good afternoon, everyone. Uh, some of my topic is not very much related to electric vehicle. This is linked with today's renewable thing, which we have been hearing since morning. That looking into the decarbonization focus, where the target is to reduce the 1.5 degrees C by 2040. All the government, all the industries are looking at that on the renewable side to the larger extent, right? And as we are hearing that there are large number of electric loads are increasing primarily due to electric vehicles on account of heating and all these. And if we look into today's emission scenario, as on today, if we look into more than one third of the emission is due to the generating resources only, even if we have penetrated so much renewable in last few years, as we are hearing. So would just like to focus, means we have been talking on renewable solar and wind penetration, all the grid connected solar and wind plants. What are the key challenges which we look into when we are integrating solar and wind? And again, I repeat, as we are looking into the demand growing due to all the electric vehicles type of thing, obviously like we have to put more renewable generations so that obviously we don't put much pressure on the fossil fuel side. So what are the key challenges when we are integrating more or more renewable into the grid? Because all the renewable are the grid connected. The first and foremost important thing is, obviously, as we all know, that renewable are intermittent in generations. Like we are talking about solar and wind. Solar as well as wind, both are dependent on the conditions, right? Solar, obviously, maybe like we can say that during the day is stable. Wind depends on the wind blow. As solar all depends upon the solar insolation and the reason at the particular day, on the particular month, in the particular year type of situation, right? The other key challenge which we need to understand, means I would be just slightly touching the technical side also, that if we look into whatever our existing conventional generation system, they have their inbuilt rotating inertia. But all the renewable, when we talk about the electronics, don't have the inertia. And when we don't have the inertia, without doubt, means there is the issue with respect to the grid stability, grid reliability, because as we know, means as a layman if I say, if we know that if there is a mismatch between the generation and the demand due to any reason, there may be the frequency variations. So this is one of the biggest challenge as we are penetrating renewable as much in the grid. Obviously, like we have to look into that how the system has to be fast enough to respond for power resilience, stability resilience, right? One thing is reliability, other thing is the stability. Frequency regulations, voltage mismatches, grid stability, all these are the key challenges which are happening with the renewable penetrations. Transmission system, I'll say, not line, the transmission system reinforcement. If we look into the renewable scenario in US, the projects which are in inception and in development stages in 4 years, they have the longest queue for getting the interconnection agreement with the grid. Because transmission system, interconnection systems are being so congested with the renewable that, say for an example, if we look into the California region, there the 40% is renewable, 60% is conventional. So as much as we are putting renewable, obviously we are putting grid primarily into the unstable region unless we support this by doing something. So what's the solution? Solution is primarily like the key solution is energy storage. And when we talk about energy storage, that's the reason that if we look into integration of energy storage is becoming very important nowadays within the grid, so that we can make system more reliable even the post integration of renewable. We increase the response time as far as the grid resilience and system resilience is concerned. So now when we talk about energy storages, means obviously like energy storages can be of independent. For an example, like if we look into the plants in US, primarily like Tesla type of companies have altogether standalone very big 400 megawatt, 600 megawatt capacity of the battery energy storage system plants. But most of the renewable plants are coming as a hybrid plants, like when we say solar plants, along with the energy storage plants. And what's the reason? Reason is, say for an example, in the particular region, someone is putting the 200 megawatt of the solar plant. And as the renewable penetration is increasing, when the demand is at low, but the solar plant can generate 200 megawatt. Since these are not dispatchable plant, obviously the power has to be curtailed. Means even if the plant can generate 200 megawatt, but due to the lesser load, due to the lesser demand, the generation has to be curtailed. Means even if the generation is free of cost, has to be curtailed. There are cases. There is a very one famous diagram which is called as a duck diagram, which is primarily relate the PV, means I don't have the slide because I didn't mail it, so I'll just explain. This is the diagram which is by California Independent System Authority, that there are cases that during the day in the California, the fossil fuels plant has to go down. And as we all know, I believe that the coal-based plants are not designed for the cyclic duration. We can't shut down the coal-based plant and we can't restart the coal-based plant in a day. Even for the combined cycle gas-based power plants, if we have to operate the plant, that the plant is in their efficient operation from the carbonization point of view, we can't go below the 20% of the generation. And when I say 20%, this is the most technological advanced combustor system which is being used in GE and Siemens type of gas turbines. That if we go below 20 to 25% of the generation, obviously like our emissions from the gas turbine increases significantly. So what does it mean? Means we can't shut down the gas-based plant, we can't switch off the coal-based plant. These are not designed for frequent shutdown, start and spinning type of cases. So obviously like we have to curtail the solar plant because we have to keep this operating. So what does it mean? Means we are having free generation. We are getting more or less free energy from the grid. So the most important energy storage system which is being used nowadays is battery energy storage system. Obviously there are a lot of long-term, long duration energy storage system, what I say, of different technology like mechanical type of systems, electrochemical, primarily the battery energy storage system is electrochemical systems. If we look into like in mechanical nowadays, the compressed air energy storage system is the very long duration energy system and is technically already the technology is matured. Pumped hydro storage, as we have already listened since morning about the pumped hydro storage, all these are considered as the energy storage systems. But then there are challenges. If we talk about compressed air energy system, as far as I am aware of, post 98, even the technology is matured, there is no compressed air energy storage system which came under operation beyond the 200 megawatt of the capacity. Because in that particular system, air is compressed, stored in the underground cavern, and then the air is again pumped to the turbine with the heated fluid. One of the very famous technology nowadays is the molten salt technology, which is very common in the concentrated solar plant. The plant which we call as a solar thermal plant, not the solar PV plant. There the heated energy is stored in the salt and then heated energy is feed to the fluid and the turbine is rotated. Pumped hydro storage, we all know the bigger challenges like obviously the plant sites, topography, environmental issues and longer gestation periods. So one of, even like if we look into number of projects in the energy storage space, maximum number of projects which are coming since last 5 years are the battery energy storage system. As we all know that lithium ion technology has matured so good in terms of cost. If we look into statistics, now the cost of battery energy storage system came down to around $380 to $400 per kilowatt hour. Again, that's the same. Like someone told in the morning that I think around 10, 12 years before we were hearing that the solar generation cost is around, if I recollect correctly, 10 to 15 crores per megawatt. Nowadays we are hearing 3 to 3.5 crores. Means complete chicken and egg story, like manufacturing and demand. At that time we were having no module manufacturing because we were all importing the module. Similarly in the battery energy storage system, lot of papers, lot of consulting research papers. One of the paper which I was hearing, like I think which was written by McKinsey last year, this states that within next 5 years the lithium ion energy storage for the larger capacity of 200 megawatt to 400 megawatt came down to $200 per kilowatt hour type of. So what happens when we use battery energy storage system? How this supports, like the challenge which I just explained with the renewable integration into the hybrid mode, how this particular system supports. Say for an example, during the day, when we have the complete solar insolation, solar plant can generate the maximum output, but load is not enough to feed it. So instead of curtailing it, the additional or excess generation for the solar plant can be used to charge the battery. And when the peak load is there, when the peak demand is there, the particular BESS can discharge, because nowadays the battery energy storage systems are coming for 6 to 8 hours duration. 6 to 8 hours of the battery energy storage system plants of the 400 megawatt to 600 megawatt are in commercial operations in US and Australia in a big way. So during the peak demand, this battery energy storage system can discharge and can take care of the load. Other thing which I told is the challenge related to the frequency. This is very big challenge of the frequency support, because say for an example, in the solar plant, if the load increases, solar plant is not able to support, frequency will go down, because these doesn't have their own inertia. So how battery energy storage system can support it? The response time of battery energy storage system to be on the line in the milliseconds. So obviously, as soon as there is a sudden load, we have to support it. Instead of ramping up the conventional machines, battery energy storage system immediately takes care of the increased load. So that, like similarly for the voltage support, at a lot of places for the reactive power support, for the voltage support to keep voltage within the stable region, battery energy storage system is playing major role. Only thing is, this depends that what is the location of that particular system. Like if this is connected at the transmission level, then obviously this takes care of the voltage injection as required. How this takes care of the transmission line congestion? I think in India also we know, like sir may be knowing, that the bigger challenge is to have the transmission line augmentation in pace with the generation. And in pace with the generation, and moreover in pace with the renewable generation. Because unless we have the spare capacity in the transmission system, we have only the option to curtail the generation. Otherwise, this excess generation can feed the other factor of the region. So this takes care of the transmission line congestion, deferral of the transmission line augmentation, which is a big cost if we look into. So from all these perspectives, that battery energy storage system supports it. The last thing what I would like to cover is from the energy storage point of view. This is not only for the grid connected model. A lot of industries are looking into the captive plant with the concept of 100% renewable. So obviously when they are looking into 100% renewable net zero target in India, the largest refinery of India is having the target to be operating on net zero by 2035. We know that, right? And that largest refinery load is around 1500 megawatt. So only solar and wind combination can't run the refinery which is supposed to be run on the continuous operation, right? There has to be some energy storage system. That is battery, hydrogen storage, converting their turbine, making it compatible to run on the hydrogen. So all these energy storage are becoming quite important from the captive net zero targets perspective. One of the very recent study, which Bechtel, means I'm just leading that particular project, there is a very big LNG project in Australia where the load demand is around 800 megawatt. Plant wants to operate it 100% on renewable. So that plant is being commissioned with reciprocating engines of Wärtsilä, because Wärtsilä has the hybrid generation model where the reciprocating engines can operate along with the solar PV and battery energy storage system. Why battery energy storage system? Because this is the LNG plant, continuous operation plant. If there is a cloud cover, right, solar PV generation will be down. So engine will take around 10 minutes to be on the line to ramp up. So for this 10 minutes, that battery energy storage system can take care of the loads. So last, in conclusion, means why I'm just trying to focus on so much on the energy storage, because we have been talking on renewable, we have been talking on adding the renewable, but without the energy storage, don't think that renewable can be sustainable. We have to look into the energy storage space as well, the options, the maturity of the energy storage technology, what type of technology fits where, and that's the only solution from the system stability and resilience point of view. Thank you.